Good morning. My name is Andreas Fertig, and I work as an independent trainer, consultant, and occasional speaker. I'm also the creator of C++ Insights, and I'm very happy that I will have own talk on this tool tomorrow. I will use it today, and if you don't know it, I will introduce it to you briefly. The topic of today is C++ and Lambdas Demystified. Before we start with C++, let's talk about another language, German. My last name is German because I'm from Germany. And Fertig has quite a few meanings in English. It's like finish, finished, complete, or completed. That's a really excellent name to be on someone's project. And you can't pay me a fortune to find out that the name doesn't make your project finish in time. Other things depend on that than my last name. But I'm happy to take your money, really. While I'm having started to talk about my last name, to introduce it, I collected a couple of stories about it I wasn't aware of before. So I can now tell you that Johannes Drostrup is able to at least read German, because he understands my last name. I also learned when I presented at NDC Oslo that in Norwegian, Fertig is also a word spelled and spoken slightly different. If I get it right, it's ferdig, fertig in Norwegian, so close. That's cool. I'm very unhappy to have to tell you that nonetheless, it's a very common German word because we use it often. I mispronounced my own name for about 30 years. In proper German, it's pronounced Fertig. At the end. Well, with the dialect where I come from, I pronounce it most of the time Fertig, with a hard K at the end. It's wrong, but there is no such word in German, so all the people get what I'm talking about. All right, enough German lessons. Let's talk about lambdas and the evolution of lambdas. If you look at this picture from the left to the right, we have first the so-called capture list. And in C++ 11, we are able to capture by copy, by reference, by named copy, by named reference. We can also capture this. And we can capture parameter packs. In C++ 14 then, that got extended, we can now have something called init captures. We will have a look on that later. It's the first version in the C++ 14 line. We can introduce a new name while capturing a variable in the Lambda. And we can do this again via copy or via reference. In C++ 17, we got the ability to capture this star or star this or dereference this. We will also look into this and where it can help you. Next to the capture list, we can now see angled brackets. And angled brackets give us a hint that we are now seeing something which is related to a template. And in fact, we are looking at a C++ 20 feature. The glass bowl is right from me. Then we will have templated lambdas in C++ 20. We will also look at this. Next to the angled brackets, we have the parentheses, and in that parentheses, we can specify the parameters the lambda takes. In C++ 11, that could be an arbitrary type like int or our own class type whatsoever. In C++ 14, this once again got extended. We can now say they are auto. It's a parameter type. And concepts not covered, this is the only part where you can say auto as a parameter type in a parameter list. We are talking then about generic lambdas. I will show them to you. Next to the parentheses, we have the specifiers like mutable. In C++ 11 already we can say that a lambda can modify its captured contents if copied if captured by copy, and then we need mutable to allow this lambda to change the captured variable. In C++ 17, we got const expr. So const expr, all the things also apply to lambdas. Now we have implicit const expr lambdas. I will show some examples about that to you as well. With C++ 20, we will get something in addition which is called const evil. And as I'm not a native speaker, I hope I do not say it's evil. It comes from evaluated, and it means that this function then in fact will be evaluated at compile time, period. It's a new thing, it's a little bit related, or it's related to reflection coming probably with 23. So this is the first sign of it. Next to that, we can have the exception specifier with no except. And unfortunately, I had to cross out the ensure and expects because there are no contracts in C++ 20 anymore. I hope you've heard of that. If not, it's an entire discussion of its own. After that, we have the trailing return type where we can specify our return type of the lambda. It can again be an int or any arbitrary type. We can omit it usually, but sometimes we need to be specific there. After that, once again, C++ 20 appears. There we can say requires, because we have concepts in C++ 20, and lambdas will also work with concepts. Then below that, in the curly braces, we have the lambda body, and after that, in the parentheses, we can pass the parameters to the lambda when we invoke it. So it's roughly the evolution of lambdas. We can see that they, in fact, got changed and updated with every standard. So they are still hot. Now I have a question for you. Looking at this piece of code, only 4 lines. It's a complete program. Valid or not? If you like to take just one thing from this talk, then the right answer is always, it depends. It depends. In C++ 20, as far as it goes now, this is in fact valid. It's an empty lambda which captures nothing and is default initialized because it's default constructible. There is discussion to disallow it because it's nice to show it on a slide, but more than that, maybe no use. Let's have a look at lambdas and the internals. Here I have a jar string saying, hello NDC TechTown. And then I have a lambda below which captures the string by reference and has a printf in it to print out the string. Now what does this really do or mean? And this is the part where I switch to C++ Insights. Who has heard of C++ Insights already? All right, great. C++ Insights is heavily inspired by Matt Godbol's Compile Explorer. So the second question is, who has heard of Matt Godbol's Compile Explorer? Okay, who hasn't heard of it, go check it out, godbold.org. Anyway, what you can do here in C++ Insights is type your source code into the left, and at the right, you will get a transformed version, an enriched version. And this version will show you all the great things, most of the time, the compiler does for us. And in this case, I can visualize what a compiler does for this lambda. And what we can see here is, all right, it first starts with the compiler generating a class for us, because the closure type of a lambda is a class. Next, the compiler takes care that all the variables I like to capture are in this class. They become class members. In this case, it's an array of references of type jar, const jar. And then we have this part, and this is where our lambda's body goes into. So it's a little bit of syntactic sugar. What we've written on the left, the printf, now goes into the call operator of our closure type. And they're in the call operator. And that's why we can now below here invoke this call operator and with that call the lambda, which is essentially what I'm doing here on the left with the parentheses. So it's basically syntactic sugar the compiler does for us to transform a lambda into an already existing feature set of C++. So they may be new at the top and they may have cost compiler vendors a lot of work, but internally they use just the things we already had, which I think is brilliant. Now, while I developed C++ in Sites, I had to work with a couple of strange examples, and lambdas were the hottest topic, the things people are interested the most, and so I tried to get them right, and it took me several times, and I'm not sure if I've succeeded or finished there. And this is something I came up with when trying to figure out where lambdas can appear. And the question to you is, in how many places here can I have a lambda? I'm not saying that's sensible or that's code you write on a daily basis. I really hope not. It's just a question, how many can appear there? How many places, if you do not do recursive lambda in lambda stuff? Just give me a number. Let's say from 0 to 8 or so. I have 5. Anybody willing to agree to give a lower number or a higher number? 5 is in fact the correct number, because I can have a lambda to initialize my variable x. Makes no sense, but I can do it. Next, in the for loop, I can have a lambda in the initializer, just printing out something. And then, of course, I can use a lambda to decrement x in the condition of the for loop. And in the end, I can have another lambda in the for loop doing what we usually do when we increment. It just prints out after. And then, of course, in the body of the for loop, I can have another lambda wrapping the printf. As I said, doesn't make much sense, but these are all the places where lambdas can appear in this example, which is a lot. Let's look at another example. What happens if we capture a global variable, like here? I have my int x, which is initialized with 2, and then I have main, where I use a lambda to capture x and increment it. And some feedback I'm getting sometimes is the code does not compile, because I'm incrementing x without having said that this lambda is mutable. Let's use C++ in Sites once more. And let's transform this thing. Now we see once again, okay, compiler generates a class for us, and in fact, in the call operator's body, it increments x by 1. As a side note, all the time I can transform this code means that it compiles. Okay, so that code compiles. What you can see here, or what we cannot see here, is this lambda captures nothing. X is not captured in this lambda. And that's the reason why I can increment X. The compiler is smart, and on our side, there is no need to capture X and to increase the size of this lambda, because it's a global variable. You can access it from everywhere in this compilation unit. And the compiler knows that. Sometimes this bites us because we overlook the fact that it's a global and we increment it and we see side effects outside of the lambda or things like that. So that's feedback I got in the past. But in general, the compiler is on our side and tries to provide us with small and fast code. We can also use lambdas together with function pointers. So we have here the signature of a function pointer returning an int, taking an int and a char as arguments, and we can assign a lambda to that function pointer. An application area for that can be legacy APIs where you have to deal with regular function pointers, and now you can still pass or can use a lambda to initialize them. And you do not have to change the legacy API. If we once again look on the internals, then the question is, how does this work? And this works because it's a captureless lambda. This only works with captureless lambdas. Because for captureless lambdas, the compiler creates us this function, which is called invoke. Compilers are free to choose a name for that. And if you look at this, then you see that the body of this invoke function is in fact the same as for a lambda. Can prove this because it's right here. And then there's a second thing. It's a conversion operator we are looking at here. And that returns this static invoke function. And if we now look down here while initializing this function pointer, then we can see that, in fact, in this whole call chain, this conversion operator is called returning that static function of the lambda. And with that, we can assign it to a function pointer. That's again nothing magic. We can do this by hand. We could have done this before. Just how lambdas interoperate with our code and with the existing features. By the way, if you have any questions, feel free to raise them. Because I have a question, maybe multiple questions. Here I have some example code. I have three variables, a, b, and c of type char, int, and char. And then below I have my variable f, which is initialized with a lambda, which captures by copy, and it uses the variables a, b, and c. And for the following questions, assume that we are talking about an x64-bit platform. The question is, what is the size of this lambda? In bytes. 20? We have 20? 24? 24, 20. No. The size of this lambda so far is 12 bytes. It's 12 bytes. We have the usual padding rules. Our int is 4 byte long, and our two chars are also extended to 4 byte. So we have 3 times 4 bytes that sums up to 12. So these are the rules.
And they padded and in the same order? You
The-
get 2 bytes, padding 2 bytes, 12 bytes, padding 2 bytes, and pad the whole thing to 4. Round the whole thing.
I'm not sure if I understand the question right. So
You make a struct with 2 chars, 3 ints, and 2 chars, the size of 20, that's correct.
oh, pardon me. It's not 3 ints. It's an int initialized with the value 3. So that's why, okay, that's why you came up with 20. Yeah, okay, now I can see it. It's just 1 int, it's 2 chars, so, okay. That's 12 bytes. And I mostly work in the embedded domain with really small memory systems. So the padding wastes me a couple of bytes. And if I have to use the thing over and over, it may disturb me earlier or later. So what can I do about this? I can slightly rearrange my captures. Have you seen it? This is the previous version. This is the new version. I switched the order I use them. Instead of A, B, and C, I'm now saying A, C, and B. And with that, I reduced the size of this lambda to 8 bytes. Now it's a really simple example, and in your code it may not be that simple, just reordering the things you're using. You can use init captures to specify the order you like the variables to be captured if you are not able to restructure things in your lambda's body. Having said all that, please be aware. This is what a standard tells us about what I've just shown you. An implementation may define the closure type differently from what is described below, provided this does not alter the observable behavior of the program other than by changing the size and/or alignment of the closure type. So basically what I've shown you works today in all the compilers I've checked, but compilers are free to change this behavior because you're not supposed to observe this behavior. So it's up to you. If you have to save bytes, it may be valid to do it currently, but it may fall down later. C++14 gave us generic lambdas. Generic lambdas are the one place where you can write auto in a parameter as a parameter type, a parameter list. And with that, I can now say, okay, I have this lambda which has an auto parameter v, and I now can call it with a double or with an int. How does this work? Once again, looking behind the scenes, we can see that again, of course, compiler created the class for us. This is the interesting part. Our call operator is now a template. And our auto parameter v is just a template parameter. That's how generic lambdas work. And below here, we can see, okay, these are the instantiations. We got one for double. V equals double now. And we got another one for int. Once again, I'm impressed. Really simple, using existing stuff. What's the type of L is the question. The type of L is not known. It's the type of the lambda, the closure type. So I have to make the name up in C++ in sites because we don't know the type as programmers. That's why we need auto to capture the type of a lambda. Is that your question? Then let's chat later about it. What can we do with generic lambdas? One thing we can do now that we've learned that the parameter type is in fact the template parameter, we can apply C++ 17 features like const expr if to do in one lambda something like figuring out what is the type and what is the right thing to do. So if the type is a double, I like to return v times 2.0. If the type is not a double, I assume it's then an int, I return v times 2. So maintaining the category of the type. I'm not multiplying double with int here. These are things we can do because we can use this const expr if together with the stud is same because we are in a template effectively. Looking at another example, the dangling reference trap, how I call it. You may have come across something like this. We have our variable x, and then we have our lambda L, which captures x by reference. In the lambda's body, it returns the result of x times x, and at the end, a lot of code is in between, we return this lambda. Question, what's happening? It's undefined behavior, you say. Have you checked the standard? Because the standard has a really nice wording for this. It says, if a non-reference entity is implicitly or explicitly captured by reference, invoking the function call operator of the corresponding lambda expression after the lifetime of the entity has ended is likely to result in undefined behavior. So unfortunately, we don't know if you're right. But usually it crashes and it is undefined behavior. I have no idea what likely has to mean here because we cannot detect undefined behavior, and if it's likely, then whether or not it works, we cannot depend on it. So yes, you're right. It's undefined behavior. And we can fix this, as shown on this slide, easily by capturing x as copy. That fixes the problem. That's good. Now, let's say over the course of our development, we change this example slightly because now we need our int to be allocated on the heap. So we have a new here. We also fix the rest of the lambda, dereferencing x, and so on. Okay, works. Sort of. You know this situation, something works for a couple of times and then someone figures out, oh no, there's a memory leak in it. I know how to fix this. That's easy. We have to delete this memory, of course. Right? Calling new and delete always together. Ouch. Now I'm returning in this lambda something which got deleted. So capturing by copy may not always be that safe. Of course, you can again fix this by using shared pointers. Then the things work as expected. Be aware of these traps. Let's talk a little bit more about captures. Here I have a class called test, and in the constructor of this class, for some reason, I have a lambda which captures one of the class's members, A, and returns the result of A plus 2. It does so by capturing by copy, and just because I can, I once print the result of that lambda, then I'm invoking A in the context of test, and after that I do another printf using the lambda. Question is, and I make it easy for you, it's initialized with 2, 2 plus 2 is 4, So the question is, what is the output of the program? 4, 4, 4, 4. Do we have something other than 4, 4? 5, 5. No, it's 4, 5, of course. It's 4, 5. Because what we captured here is not A, it's the this pointer. And that refers to A. And that's why we see the effect of changing A outside of the lambda inside of the lambda. Okay, that's an unfortunate trap we can get into. Once again, there are ways to fix this. This is the star this I introduced earlier to you, or dereference this. With that, we can say that we like to capture a copy of this, so a deep copy. That means it's expensive, probably, depending on your class. And with this, the output is 4, 4, as hoped or expected. We can once again use C++ Insights to peek a little bit behind this. And here's the example, it's a reduced version. I use here on the left the star this for capturing. Then we can see on the right that in fact the lambda now contains a member of type test with the name underline this. Name is also made up, compiler has other ways to do that. If I omit this and just capture by copy, then we can see, in fact, what we're capturing then is a copy of this pointer, because this is what we usually get when we copy a pointer. Copy of the pointer. There's another way to approach this, if you like, and that's C++ 14's init captures. You can say here A1 equals A, and if we now transform this, then we can see that we have introduced a new variable in our lambda, A1, and this is the one which is used, and down here it's initialized with the original A. And that's interesting for me because once again it comes down to size. Capturing this as a copy can be expensive because it's a deep copy. You have to copy every member of the object you're just capturing or copying. So we don't know, large std string or something like this. Plus, in my simple example here, I captured 2 ints while I'm just needing 1. And in the world I live in, that's a waste of resources. So I'm more happy with this init captures. You can, if you like, use the same name again. Then we have a new int variable called A. A is used inside of the lambda. It's what you prefer, to introduce a new name to make it more distinguishable, or to use the existing name to give it the meaning that still A we are talking about. Once more, talking about the size of lambda, we have here our class test, and it's a reduced version. It has just one member of type int A, and we capture again per copy. So that means that we capture this by copy. But now we capture something more, a const int called size, to declare an array of ints of the size within the lambda. And the question is, once again, what is the size of this lambda? Let me ask differently. Is size part of the lambda? Is size captured in the lambda? Yes or no? No. Why no? You're right. So the answer is it's not captured in the lambda. I can prove it. Also, it's my tool, so it may not be the best proof, but it's open source, you can check it. Because what we are looking at here is a so-called ODR use, the one definition rule use. And we don't need size within the lambda because the, as you said correctly, size is const. So we do not need to capture it in the lambda. That's nice. More examples. It's what I call the sleeping lambdas. We have 6 lambdas here, A to F. They all do basically either capture a std string and print it out, std string called foo, or just do nothing. And there are different versions of it. Some capture by copy, some by named copy, and some by named reference. If you look really closely at this small piece of code, then you will find out that none of these lambdas is in fact invoked. They are dead code. It's a complete example. It's main. How many unused variables will I get from a compiler? Let's say give me a number from 0 to 7.
I think 7.
I have 1. You said 6? 7? Okay. More numbers? The surprising number is 3. I get 3 unused variables. That's B, E, and F. And why is that? In A, I capture by copy the std string called foo. Capturing by copy means that this std string gets copied. Copying a std string has side effects because it needs to allocate memory. It needs to copy memory from A to B. It's what we like that thing to do because otherwise we cannot copy a std string. But this side effect causes the compiler to see, oh, that thing is used. I cannot optimize this away because the constructor does something here. So A is not an unused variable. B, on the other hand, of course, it's an empty lambda capturing by copy, but it doesn't capture anything, so that gets an unused variable warning. C is more or less equivalent to A, so that's easy. D is the more interesting thing, because there I have a lambda with an empty body. But I specifically say in the capture list that I like to capture foo. And if I tell the compiler to capture foo, the compiler will do so. And with that, I'm in the same area as A. I will get a copy of that std string. And then left are the 2 reference captures, which are easy, so the compiler will see through and will figure out that they are unused in fact. Why I'm telling you this? Because this code may look very innocent, and because the impression is you're not using this lambda, it will do nothing. But it will copy on each and every time you pass it. A, for example, C and D will copy even if you do not use this lambda. From one point of view is understandable. But I've seen code where the lambda is used to print out some debug message, and the assumption was, because we are not invoking this lambda, It will not do anything to our runtime or to our resources. That's unfortunately not true. Looking at C++ 17, we've got implicitly const expr lambdas. And with implicitly const expr lambdas, I can do a thing as shown here. In main, I have an array of ints, and then I have this all-off algorithm which checks with the lambda if all of the numbers passed in are even. And thanks to C++ 17 and const expr, this code is evaluated at compile time. So you will not pay any runtime overhead for that. Now one question may appear, and that's why I'm having to show you so much lines of code while I'm just trying to show you 3 to 4. Because I'm really cool and I can show you how the algorithm is implemented. I can do it on my own. No. Unfortunately, in C++ 17, we have implicitly const expr lambdas, but our algorithms are not all const expr. So the all even or all off algorithm here is not const expr in C++ 17. It will be in 20. And this will make this code much simpler in 20 because I do not have to show you all the boilerplate code. I can just show you what I like you to show. Now we are down to 3 or 4 lines. Where can we apply or how can we apply lambdas? These are examples from C++ insides. There I have a function called wrap in parents or curlies. And what it does is essentially I have a lot of code which needs to be wrapped either in parentheses or in curlies. If you make up an initializer list or a function call, then there are parentheses or curlies involved. And there is some code before and some code after to generate these braces and the correct type of the braces. So before I used to write this function, I had this, well, is it a parentheses or is it a curly, all over the place, opening and closing. So it was duplicated code all over the place. Using a lambda, I can now say, okay, I have this wrap in curlies or parentheses function, which I tell whether it's a curly or parentheses I need, and then I pass a lambda. And this lambda can now fill the space between the parentheses or the curlies. So what I really need. So that dropped a lot of lines of code in the implementation. Another thing I have is for each argument. So often if you write programs, we have parameter lists when you call a function, when you write a function, and I have to make that up again. So I have to comma separate these lists, and this is a function which does this for me. And it's once again, I do some code before, and then I loop over a list, over an array. And I either insert a comma, invoke the function, or do not insert a comma. Because for the first element, no comma is needed, and so on. So this again dropped some lines of code. One thing I also like is what I can do with lambdas is make more variables const. I like const really much, and I like my variables to be const. And pardon. This is an example how I use it to make a std string const, because this std string is either initialized with a global value or with something made up. So it depends whether it's a lambda we are looking at, then I have to say operator in front and do things a little different. Or if it's a regular class method, then I can just return the name of this method. There are different approaches. I can initialize my std string either empty or with the more likely if branch. But then it's not const. Wrapping that whole thing in a lambda and returning either A or B from that lambda enables me to have the std string being const. That's, I believe, partially taken from maybe JavaScript, where it's called immediately invoked function expressions, so it's a not so new technique. If you program on the Linux or with the POSIX API, you may have come across code like this. I have a read data function here which opens a file, that open returns a file descriptor, which I check whether it's -1, so operation failed, then I return 0, or not, then I can read from this file. I can check whether this read was successful, then I can truncate this file because I've already read it, and then I close this file and I return the length, probably casted with an error cast. Do you see the bug? Please.
File descriptor leak.
I have a file descriptor leak in line, what's it, 13, because they are returning 0 without closing the file descriptor. Excellently spotted. What can I do about this? Well, I can be more careful, of course, but I can also use a couple of utilities. I can say, okay, I have here a class called final action, and I create a variable out of it called cleanup, and to that class I pass a lambda. And this lambda checks whether fd is not equal to -1, and if so, it closes that file descriptor. Now, what's the implementation of final action? This is the rough implementation of final action. It's not from me. If you have heard about the guideline support library, you can check it out. It's in there, much more verbose and suited for more use cases than that simple one. But it boils down to being a class template which has only one member, and that's of type T, the type you instantiate the class template with. It's called maction. And in the constructor, this thing you pass in to the constructor is moved into maction, into the member variable, and that's it. So essentially, I'm storing the lambda in this class, and the brilliant thing is I'm invoking it in the destructor. So every time I leave scope, the destructor kicks in, and my lambda is called and can clean up stuff. And I like that much more than being really great at spotting the things where I miss the close, because now I cannot miss the close anymore.
Is something you wrote yourself as part of standard library?
It's not something, the question is, it's something I wrote myself. I may have wrote it before, but it's publicly available as the guideline support library, if you have heard of that. Microsoft has an implementation on GitHub, so it's there. It's much more verbose, suited for more use cases than this one. But
it's not part of standard library.
It's not part of the standard library, no. No. Looking at C++ 20, we can now have Lambda captures that capture pack expansions and apply move to it. And that's new because we can now efficiently capture a pack in a lambda's init capture list and move it to save resources. I have an example here to show what it can do. I have this invoke later function which I pass a std string to 3 std strings, hello, space, world. And this invoke later function is a variadic template which inside returns just a lambda which captures all the variable arguments, margs here, the variadic pack, and applies std forward to them, to each of the arguments passed in, to forward them, preserving the value category inside of the lambda, and the lambda later on then, if you invoke it, calls foo, passing once again the arguments now inside the lambda, and with that we can move that std string efficiently into the lambda without having to copy it when it is captured. And that's new in C++20. You, before that, were able to capture parameter packs, but you could not apply functions like stood move or stood forward to each of the captured variables, arguments. We will also have templated lambdas, and the question is, what are they good for? I mean, in C++14 we have generic lambdas, so I can write a max lambda which figures out whether x or epsilon is the greater one and returns that one. So I can call it max with 2,3, it works, and I can call max with 2,3.0. That also works, but it's not correct, because now I'm either returning an int or a double, so I have some cast, some implicit cast the compiler does for me. And with templated lambdas in C++20, I can fix that thing. I can now say, okay, I have a type name t that lambda takes, and my both parameters x and epsilon are of that type t. And with that, I'm in the same road as we can go with usual templates or function templates. I can now say that both parameters are of the same type. That's something I cannot do in C++14 with auto. I can also use this to, for example, say, okay, my lambda takes a stood vector of type t. So we can use it as a regular template. And I can also say, okay, my parameter type can also be a non-type parameter type, for example, size t. Saying, okay, this lambda takes a stood array of type int and with the size n, and the size n is determined by the compiler through the template. So this enables us to do a lot of new things. And now one can come up and can say, but I can do this in C++14 already with auto. Does it compile? Once again, the answer is it depends. In GCC it does. In Clang it doesn't. As far as it goes, I know that there is something, either a feature or a bug in GCC, because in GCC you can apply auto to every function, not just to templates. I'm not sure if that's because we are looking at concepts and there is some check missing, and this is why in GCC this example compiles. I believe it's not valid C++. I trust Clang more on that side. Once again, with C++20, we will have default constructible lambdas which can be used in a decal type expression. And that makes things really funny. So imagine having that stood map which you like to equip with a custom comparison operation. So in C++17, I have to write compare. I create a lambda which compares x and epsilon, and then I have to say that my stood map is of type stood string, of int, and of decal type of compare. That works, of course. Thing is, now I have this compare variable leaking around. It leaks in the JSON scope, is accessible after the stood map, and the only reason it's there is for this stood map. So I would more like to have it where it belongs to, together with that stood map. And that's something I can do with C++20, because I can now move this lambda into the decal type expression, saving me coming up with a name, That's always good, because naming is hard. And it's now together, where it belongs to. The comparison operation, this lambda now is directly coupled with the stud map. After all that, examples of lambdas, one question may remain, can we overuse lambdas? I mean, they are great, they are interesting. And oh boy, yeah, we can. That's an example I've written on my own in C++ Insights. I stumbled over it when preparing the talk. I have a lambda here to initialize a bool, and all that lambda does is essentially returning a value. Applying a lambda here is nonsense. I had something else in mind, or I refactored that example in the past. I do not remember, but just this statement, it makes no sense to have a lambda here. I can just return that value and initialize this variable as usual. So yes, we can overuse them. And as far as I know, there is no check from the compiler telling me, well, that's a little nice that you try to apply lambdas here, but also a little stupid. Maybe that will come. So I can just write this that way and everything is fine. If you're interested more in that topic, there's a lot of work of others. So there's a great talk by Björn Faller, who has talked today or tomorrow also here about high-order functions for meeting C++. There are a lot of C++ weekly episodes from Jason Turner, who is also here. There is an excellent blog post by Vittorio Romero, and there are a bunch of other things, so it's totally incomplete list. Feel free to look at that. So far, it's been a pleasure giving the talk to you today. I will be around for questions. We have a couple of minutes left, or later at the conference. There remain 3 words to be said. I am fertig.